So onto our sixth rule with polyatomic ions, also referred to as oxyanions. And from the name, oxy meaning containing oxygen, and anions being of a negative, possessing a negative charge. So unfortunately, these polyatomic ions need to be memorized. Okay, and most of them have like I said, a negative charge. Most of them are negatively charged. Just from the word polyatomic ion, what it means is that it is made up of more than one atom combined. So now we're dealing with not just two single elements combining, but already a compound that is an ion. And if we have a look at them, these polyatomic ions, we can see them over here. These are some of, not all, but some of the most common ones, such as ammonium, nitrite, nitrate, hydrogen sulfate, hydroxide, cyanide, permanganate, hydrogen carbonate, etc. These all need to be memorized. They must memorize. Okay. You must memorize these. To give you a quick example of making use of ammonium there, let's make use of the reaction with nitrate to make ammonium nitrate, which is a common fertilizer. So ammonium nitrate is a common fertilizer. Common fertilizer. And ammonium's formula, as we saw up here, is NH4 plus, 1 plus. And nitrate, so in the reaction when they're forming, nitrate is also just over here on our polyatomic ions list that needs to be memorized. It is NO3 1 minus. And they form a compound called ammonium nitrate, which has the formula NH4NO3. And as you can see, that's the balanced chemical formula, and the charges have balanced each other out, and it is now in a neutral, stable state. Right. Then the tricky part, even more tricky, with polyatomic ions, is the following. Now, if we go back into our table that needs to be memorized, and we take a look at this chlorite, chlorate, perchlorate, hypochlorite, we can see that there are differing numbers of oxygen atoms that are within these compounds. And those different numbers of oxygen atoms dictate or tell us how the name of the compound changes. So we can see here that the charges are very, very similar, but as we go down the table, as we go down the table, we are increasing in the number of oxygen atoms that are taking part in, as we go down the table, as we go down the table, we can see that there are different numbers of oxygen atoms taking part in this compound. So chlorine here has 4 oxygens bonded to it. Chlorine here has 3 oxygens bonded to it. Chlorine here has 2 oxygen bonded to it. And chlorine here has 1 oxygen bonded to it. And this will dictate the name that we apply to it. Okay. So just to go over that again, and just to go over what you have to know, is the following. So there will be a prefix and a suffix that can be applied in different situations, or in different compounds and different numbers of oxygen atoms. So if we take chlorine, for example, non-metal chlorine, the name is as follows. It will be the names are as follows, going from the smallest number of oxygens to the highest number of oxygens, because remember, we're dealing with oxyanions or polyatomic ions. So per chlor 8. So we have our prefix and our suffix, and perchlorate is ClO 4 1 minus. Sorry, we're going from highest to lowest, not lowest to highest. Then we, if we take a step down to the next number of oxygens that are bonded to chlorine, which is 3, we see that the name changes to chlor 8, and we leave out the prefix. Moving further on, when chlorine has only 2 oxygen atoms bound to it, now the name changes to ITE, and it becomes chlorite, losing more oxygens. The name now gets a prefix, hypo, retains the root name, and ite is used again. So this is the specific naming for chlorine. Will be perchlorate, chlorate, chlorite, and hypochlorite. Now these can be applied to a number of the different polyatomic ions, and as you can see, you have some examples in the table that you need to know. This table, I would say, for grade 10 is possibly all that you would need to know. So sulfite, for example, let's have a look at that one. So we see we have a chlorite, which has 2 oxygens, and here we have a sulfite. So the ending is the same. Chlorite and sulfite. Okay. Now, the same rules can be applied as we've just had a look at. So sulfite, if we add one more oxygen to the sulfite, we know that the name changes to sulfate. Sulfite to sulfate, as we have done previously in our example here. So the lower number of oxygens gets the ite ending, and the higher number of oxygens, doesn't matter which element we're looking at, the rules stay the same. So it is ite and 8 endings. Okay. To do one more example, to make things completely clear for you, we can take into account this IDE ending when it comes to the non-metals, the ending of a non-metal. So if I can move over here to show you more clearly, and let's take an example. Let's take the example of phosphorus. So phosphorus, you can see that it's just the name of the neutral element. Then if I start using our IDE ending, when it becomes an anion, for example, when it becomes an anion during ionic bonding, now things change a little bit. So the name changes from phosphorus to phosphide, IDE ending. And that is going to be phosphorus. As you know, it'll be a 3- charge and it becomes an anion. And you know that it becomes a 3- charge because of its position on the periodic table. Again, staying with phosphorus, if we're now looking at its polyatomic ion or oxyanion, it becomes phosphite, and that is PO3- anion. And when it has a higher number of oxygens, it only has 3 here. When it has a higher number of oxygen, it becomes phosphate. And that'll be PO4- anion. Sorry about that being a little bit untidy. Okay, right, guys. So that is a look at the rules for naming ionic compounds with the use of polyatomic ions or oxyanions, as well as the use of the transition metal Roman numerals. And they take into consideration the valency when it's bonding with a nonmetal, and then the 8 and 8 ending take into consideration the polyatomic ions when the ion is formed with different numbers of oxygen atoms. Right, thank you.